For this last example, I want to remind you, when it comes time for our test, if I decide to put a question like this on the test, that you are required to show all of your steps in order to get to a correct answer. And I point that out because this particular version of this question is a relatively easy problem to do in order to kind of get a common sense answer. We're asked to find two numbers whose sum is 11 and whose product is as large as possible. Now, I'm not asking you to solve the problem this way, but geometrically what that means is it means let's create a rectangle where from this side to this side, if I add those two sides together, I get 11. This problem is saying make the area as big as possible. And I'm hoping it's clear that to make the area as big as possible, a square is your best bet, which means 5.5 and 5.5 on each side. And that is actually going to be our correct answer. But I would expect to see you actually translate this into a function and find the minimum besides just sort of taking a guess at your best bet. So, in order to do that, we're talking about two numbers here. So we want to define these two numbers in symbols. So we have one number, we have the second number. If the first number is x and their sum is 11, the second number is 11 minus x. This is the same trick we've used a bunch of times on things like mixture problems and lots of situations where we could add up the distance someone traveled and we knew it was 200 miles but didn't know either distance. We said one's x, one's 200 minus x. Same thing here. One of the numbers is x, the other is 11 minus x because we know their sum is 11. Now, if we want to talk about their product then, their product is when we take one number times the second number. Product means multiplication. So in terms of x, that product is x times 11 minus x. Or in other words, 11x minus x squared. In yet other words, negative x squared plus 11x. If I want to find the x value that made the product as large as possible, I could take the opposite of b over 2a. That's negative 11 over negative 2. That's 5.5. If I plug 5.5 into this, I get 5.5. So my two numbers are 5.5 and 5.5. Now I wanted to walk through this example to point out that this is a situation in which we are making the product as large as possible. We're only being asked about the numbers. We were never asked what the product was, so we never needed the y value of the vertex. But I could make this problem a little bit trickier as far as from the geometric standpoint, that maybe instead of the geometric problem of a square, maybe I have a three-sided diagram. Because maybe I have a situation where there's a river flowing over here, and I want to fence in an area next to the river, so I only need three sides of fence. And let's say I have 500 feet of fence. Well, at that point, my side lengths could be x, x, and 500 minus the two x's that I already have. So that now the area would actually be x times 500 minus 2x. If I wanted to maximize the area of this situation, it's not as simple as saying it's going to be a square. Because really, we want to make use of as much of the river as possible because it's free. So anyhow, I want to point that out because I gave you a simple problem up here, walk you through the process of how to solve it, but you could be asked more complicated questions like this one as well.